cs407, Introduction to Numerical Analysis, Naive Gaussian Elimination. The title naive, or the word naive, refers to something that's extremely simple and trusting. And we'll see in section 2.2 why this extremely simple and trusting approach is going to get us in trouble. But for right now, it should work. The chapter begins with an example of a simple electrical network. It's governed by a system of linear equations. I'm pretty leery of wiring anything like this myself, given some bad experiences in electrical engineering. However, the example does illustrate that there are some good uses for linear algebra out there. So, one of the fundamental problems in many scientific and engineering applications is to solve an algebraic linear system of the form A times x is equal to b for an unknown vector x, where you have the coefficient matrix A and the right-hand side vector b. You know the coefficient matrix and you know the right-hand side vector, and you want to find the solution for the vector x, which is the solutions. These arise naturally in a lot of applications, such as approximating nonlinear equations by linear equations, and for differential equations by algebraic equations. The cornerstone of many numerical methods for solving a variety of practical computation problems is the efficient and accurate solution of such linear systems. Note that not all systems have solutions, or the solutions to those systems may not be unique. And we'll get into where you might not have a solution. So, Gaussian elimination is the standard method for solving a linear system by using a calculator or a computer, or even doing it by hand. You're likely to be familiar with this method since you've taken Linear Algebra Math 311 here at UH Hilo, and also this is the simplest approach to solving these systems by hand. Here we're going to assume that the coefficient matrix A is n by n, and it is actually invertible. That's a non-singular matrix. When the system has no solution, we'll need to use some other approaches, such as linear least squares, but we'll wait until Chapter 9 to discuss those. So, take a little closer look at naive Gaussian elimination. In pure mathematical approach, the system of the problem A times x is equal to b is simple to find. Basically, we want to find x is equal to A inverse times b, where A inverse is the inverse matrix. In most cases, however, it is advisable to solve the system directly for the unknown vector x, rather than explicitly computing the inverse matrix. Sadly, it can be a daunting task for even the largest and fastest computers to accurately solve an extremely large system involving thousands or millions of unknown. On a positive note, though, this makes for a good benchmark to see how well your computer is doing. On the negative side, it means that we can have trouble when it comes to solving some important equations and doing some practical applications. This leads us to several interesting questions about these types of problems. First, how do we store such large systems in the computer? How do we know the computed values are correct? What is the precision of the computed results? How can this algorithm fail? How long will it take to compute the answers? And what is the asymptotic operation count of the algorithm? We'll continue these questions on the next slide, since there seem to be a lot of them that can be found on page 70 in the blue call-out box. Some more questions. Will it be unstable for certain systems? And can this instability be controlled by pivoting? Pivoting basically means permuting the order of the rows in the matrix. If we can use pivoting, which strategy of pivoting should be used? And how do we know whether the matrix is ill-conditioned or whether the answers are accurate at all? So, Gaussian elimination works by transforming a linear system into an upper triangular form, which is then easy for us to solve by back substitution. It's equivalent to finding the factorization A is equal to L times U, where L is a lower unit lower triangular matrix, and U is an upper triangular matrix. This factorization is especially useful when solving many linear systems involving the same coefficient matrix, but have different right-hand sides, and this occurs frequently in a lot of various applications. Sometimes the coefficient matrix A will have a special structure, such as being symmetric, positive definite, triangular, banded, or a block. And when the coefficient matrix has predominantly zero entries, the system is said to be sparse. In most cases, the general approach of Gaussian elimination with partial pivoting needs to be modified or rewritten specifically for the system to make it faster. For example, with sparse systems, we can use iterative methods that involve less computer memory than the Gaussian elimination. Triangular and banded systems are covered in section 2.3 of the text, and we'll get to those pretty shortly. Let's take a look at a general linear system. For right now, our objective will be to develop a good computer program for solving a system of n linear equations and n unknowns. And in particular, it'll look like this. More compactly, we can write it in the form of a summation of the individual coefficients times the solution vector, or times the x vector is equal to the b vector. In these equations, we assume that a, I, j, and b sub I are prescribed real numbers and that the unknowns x sub I are to be determined. Subscripts on the letter can be separated by a comma for clarity if necessary. So there's no prescription on the notation that has to be this way. Let's take a look at an example that we can solve. Consider the following system that has 4 equations and 4 unknowns. Here we have 6x1 minus 2x2 plus 2x3 plus 4x4 is equal to 16. 12x1 minus 8x2 plus 6x3 plus 10x4 is equal to 26. 3x1 minus 13x2 plus 9x3 plus 3x4 is equal to minus 19. Minus 6x1 plus 4x2 plus x3 minus 18x4 is equal to minus 34. We can represent this in a table for simplicity, or a matrix if you will. A table works well in Microsoft PowerPoint. Let's see how to solve it. The tables mean that I don't have to deal with all those nasty subscripts for a little while anyway. So step number 1, what I want to do is I want to subtract multiples of the first equation from the second, third, and fourth equations to eliminate x1 from those equations. For example, given this matrix, I would subtract 2 times the first row from the second. I would subtract half times the first row from the third, and simply add the first row to the third row. A couple things to notice here. First, we did not alter the first equation in the process. In this context, we call that our pivot equation. Second, the resulting system that you see here in the bottom is equivalent to the first system. We haven't done anything to change the results. Step 2, we're going to ignore the first row and the first column for now. We'll keep those static. And we repeat the process by subtracting multiples of the second equation from the third and the fourth. This will get us zeros in the second column. In particular, we'd subtract 3 times the second row from the third row, and add half times the second row to the last row. And you can see our matrix is beginning to become triangular. Step 3, we ignore the first 2 rows and seek a 0 in the third column in the last equation. We can do this by subtracting 2 times the third equation from the fourth. That'll produce a 0 there. And now, this ends the phase of the algorithm known as forward elimination. The system of equations is now in upper triangular form, and we're ready to begin the second phase of the algorithm. This is known as back substitution. One of the things to note here is in our matrix here, the last equation says minus 3x to the x sub 4 is equal to minus 3. If we divide both sides by minus 3, we get x4 is equal to 1. That gets one of our solutions. Now we put x4 equals 1 in the third equation. This gives us 2x3 minus 5 times 1 is equal to minus 9. And we can solve that to get x sub 3 is equal to minus 2. Now, we can use the results for x3 and x4 to get x2 is equal to 1. And then finally, we can use all the previous results to derive x1 is equal to 3. That completes our back substitution phase. And at the end, we have the solution. x1 is equal to 3, x2 is 1, x3 is minus 2, and x4 is 1. So, that works. Let's put all of these into an algorithm. So, we're going to be using the matrix vector form in our algorithm because we're going to obviously be using two-dimensional arrays and subscripts. We can save a bit of space here by writing a vector as a transpose in order to make it shorter on the screen. And operations between the equations in this form correspond to operations between rows in this notation. We'll use those two words interchangeably. So let's take a look at the algorithm. The first step uses the first equation to produce n-1 zeros as coefficients for each x1 in all but the first equation. This is done by subtracting multiples of the first equation from the others. In this case, the equation 1 is called the pivot equation, and a11 is called the pivot element. For each of the remaining ones, we compute aij by doing aij is equal to ai1 divided by a11, the pivot element, times a1j, for j ranges from 1 to n, and we do the same thing with the b sub i's. So what we're doing is we're performing a replacement for each row using ai1 divided by a11 as the multipliers, and we perform the replacement indicated by the left-facing arrow, as you've seen in the pseudocode throughout the book. After step 1, the coefficient of x1 in the ith equation will be 0, and the matrix will now look like this. So we've got our nice column of zeros except for the first one. With the second equation as the pivot equation, we can go ahead and compute the following for the remaining equations. And from here on, we're not going to alter the first equation or mess with it in any way, or any of the coefficients for x1, since multiplier times 0 subtracted from 0 is still 0. So we've got all those zeros, why mess with them? Thus, we can pretty much mentally ignore the first row and the first columns and repeat the process on a smaller system. After the kth step, we'll have created a wedge of 0 coefficients, and the first k equations will be fixed. For the kth equation, we obviously use row k as the pivot row and akk as the pivot element. We continue this for all n equations. One big assumption that we are making, though, is that the divisors are all non-zero. If there's 0, we're going to get division by 0, and that's going to create a problem. But as soon as we've completed all n steps, that will end the forward elimination phase. So let's take a look at the pseudocode here. Here's the pseudocode for the forward elimination. Here you can see the coefficient array is stored as double subscripted array aij. The right-hand side of the equations is stored as a single scripted array b sub I that runs from 1 to n. And the solution is computed and stored in a single scripted array x sub I. So we go through, and for k, I, and j, we perform that replacement, and we perform the replacement for the b sub i's. It looks like what we've done algorithmically for the forward elimination phase, but a couple of improvements that we can make here. One of these is, since the multipliers aik divided by akk does not depend on j in any way whatsoever, we can move this outside of the j loop, and that will save us several computation cycles. Notice also the new values in column k become 0, at least theoretically, because when j is equal to k, we have aik is replaced by aik minus aik divided by akk times akk, which reduces to aik minus aik, which is 0, and we expect that to be 0. So there's pretty much no point in computing it, but what we can do is we can store the multiplier in the place where the 0 is being created to save some space. So our improved pseudocode will look like this, and again you can see we pulled the calculation of the multiplier out beyond the j loop, so we save all those computation cycles. And the multipliers are stored because they're part of the lower upper factorization that can be useful in some applications. Now we get to the start of the back substitution phase. When we begin the back substitution phase of the algorithm, we're going to have this form. And notice this is upper triangular. Here, the a sub ij's and b sub i's are not the original ones, but instead are the ones that have been altered by the elimination process. Back substitution starts by solving the nth equation, and that's pretty easy. X sub n is equal to b sub n divided by an. Then we use our n minus first equation. We solve for x n minus 1. And that one looks a little bit nastier, but again, it's something we can do because we're tracing backwards. And if we were doing a closed form, we would continue working upward to recover all the x sub I using the closed form formula found under bullet point number 3. Now, that equation looks pretty nasty, but that's why we have computers to do it. It's also why we tend to do one step at a time when we work these things out by hand. Because I don't think we'd want to do this equation every time we're solving a linear system. So the back substitution pseudocode looks like this, and again we're keeping track of that running sum and working our way back up so that we can use that running sum in the computation of further x sub i's, working all the way back up to x1. Now we put the forward and backward segments together to form a procedure known as naive Gauss. Now, I'll apologize for the scan in advance, but you can find it on page 77 of the text. The scan shows the two procedures put together, and you can see where I marked the forward elimination phase and the back substitution phase. The critical thing here is the triple loop that can be found here in the forward elimination phase of the algorithm. Here we expect all the quantities to be infected with some form of round-off error because we're doing so much in terms of computation. Such round-off error of AKJ is multiplied by a factor of AIK divided by AKK. If this factor is large enough that the pivot element AKK, the absolute value of that, is small relative to A sub IK, its absolute value. Hence, we can conclude tentatively that very small pivot elements can lead to large multipliers and worse round-off errors in terms of an analysis of this code. So, it's a good idea to test programs with problems that you already know how to solve. I would have tested on the one we worked out by hand, but the authors have other ideas. And in particular, he chooses a strange example as opposed to the one we did by hand earlier in order to demonstrate potential errors. Also to make me type more subscripts and superscripts in PowerPoint, and to introduce a special matrix. So, begin by defining the polynomial p of t as 1 plus t squared plus all the way out to t raised to the n minus 1. This is the summation of j equals 1 to n of t to the j minus 1. Coefficients of this polynomial are all 1. We can try to recover these coefficients from min values of the polynomial. We use the values of p of t at the integers t equals 1 plus I for I equals 1 through n. If the coefficients of the polynomial are denoted by x1, x2, xn, then we'll have the following formula. And aij is going to be 1 plus I raised to the j minus 1, with b sub I is equal to 1 over I times 1 plus I raised to the n minus 1. And this gives us a linear system ax equals b. We can then write the pseudocode to solve it for n equals 4, 5, 6, 7, 8, 9, and 10 as shown on page 78, and things go pretty well for us until n equals 9, where the results give us a 16,120% error. That's a bit ugly. The coefficient matrix for this linear system is an example of something called an ill-conditioned matrix. And this one in particular is the Vandermonde matrix. So this is one that's a particularly nasty problem to solve, and this accounts for the fact that it can't be solved accurately using naive Gaussian elimination. What's amazing is the trouble happens really quickly. When n is greater than or equal to 9, the round-off error that is present in computing xi is propagated and magnified throughout the back substitution phase, so that most of the computed values of x sub I are worthless. That 16,000% error makes them pretty worthless to us. In terms of error analysis, we can calculate both the error and the residual vectors for the equations. It's interesting in comparing two solutions to see how good they are. One, we can check these solutions by substituting them into the original system and computing the residual vectors. We then accept the solution with the smaller residual vector. If we happen to know the exact solution, so much the better. We can compute that. We can compare the computed solution with the exact solution. Since the exact solution is generally not known in applications, we tend to accept the computed solution with the smaller residual vector. If the computed solution is sensitive to round-off errors, for example, a no-condition matrix like the Vandermonde matrix, then even this approach will yield some problems. So, next time we're going to see where our naivete gets us into a little bit of trouble, and we're going to introduce something called scaled partial pivoting that will help us solve the problem where we get into the trouble with our naive approach.